Welcome back, Precalcsters. Today, we've learned that triangles are hard, apparently. All of this, I promise, builds up. We are talking about the circle. Now, specifically, you guys you know what circle I'm talking about. It's the what circle? The unit circle. Now, it is going to be hidden within this section, and I promise we're going to wrap back around. I'm not going to ruin how to fold a origami perfect equilateral triangle to you guys, but in this section, we are doing two big things. So we're going to start 4.2 today. Real quick, what is a radian? 1 radian. How would you describe what 1 radian of rotation looks like? Not true. That's pi, 1 pi. You need to add, quit saying 1, just call it pi. Never talk about radians without pi. I'm going to try really hard to remember not to give you any weird decimals so that you have to use the word pi every time. Like, not just you, that's a really common issue. Okay, 1 radian, not 1 pi radians. Pi radians is a half circle, though, for what it's worth. Like, you're right there. What's 1 radian? How is it defined? It's the angle that causes something very specific to happen. You form a length along the arc length, right? That's equal to the radius. Okay, now it turns out no matter how big the circle is, that's always going to produce 3.1415 blah, 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 blah for half the circle, that many radians, or 2 times that for the whole entire circle. So 2 pi radians all the time. What we're going to do is use those ideas and start mixing and mashing with degrees a bit in here as well. But we are building up to be able to discuss our trigonometric functions. Okay. I'm going to write trig instead of trigonometric. We are going to look at the trig functions, and the nice thing about this is what we're doing with the triangle is going to make it so that you never have to memorize the whole unit circle. You do need to do a little bit of memorization, or at least have the mathematical ability to work it out every time. Memorizing is a little bit easier. But we're going to define and think about these trig functions with reference to the unit circle. So I'm not even going to write it here. We're looking at trig functions. This is like the very intro to them. Our first main topic is the unit circle. Now, you are going to see the word unit. It shows up not in lower level math a lot of the time, but what makes the unit circle rather than just a circle? Something special about it. Like, if I throw a few different circles, are any of these circles the unit circle? So I'm going to tell you one of these is, and it's because that word unit. If you got to make the nicest circle, do you agree that it'd be convenient to just have the center at the origin? Like, that's just convenient for everything. 0, 0 is nice. When you think back to what you've seen with the unit circle, it always had the same radius. And every circle always has the same radius for that matter. But one of these has a radius that I would call the unit. 1. The red circle is the unit circle. So we're going to say, just by definition, the unit circle, super easy. This is the circle of radius 1. I'm going to say radius equal to 1, whose center is where? The origin. And I'm going to write the word, or the point 0, 0 instead here. Now, anytime you see unit, this is what it's referring to. The unit circle has a radius of 1. What do you think the length might be for the unit square? Why 2? So good thought. Thank you for that. What's nicer than 2? 1. It's the square of side length 1. The unit whatever is just 1 is your nice number that you have to deal with. Okay. Now for this, we have something that I'm not sure how much you're comfortable with. You know some trig functions. You might call them ratios instead. Which trig functions do you know of? If you know of any old famous Lakota chief that never existed, you know 3 of them at least. We have sine, cosine, and tangent. Did you know there were 3 more? So those are inverse trig functions. I'm not going to count those as 3 different ones. Cotangent, cosine we've already listed, secant and cosecant. Have you guys seen them? Okay, we're going to define them after we do the unit circle because I think the unit circle is going to be a little bit nicer. So, check it out. The unit circle you guys I think had to memorize last year. You might have it memorized still. Maybe. I should have brought a quiz to check. Anybody still have it? Okay, so check it out. Your beginning task today was to fold an equilateral triangle and a 45, 45, 90 triangle. Now, I'm going to do it on paper. I'm not going to fold it for you. I want, if you're interested to do it, do it. But let's just do a quick recall from some old stuff. And we're going to recall for ourselves special triangles. Now, all triangles are special in their own way, just to make sure that we're being inclusive. But there's 2 triangles that show up super frequently, so much so that when you deal with the unit circle, these are the triangles that everything is referenced from. The first of these is a 30, 60, 90. And these, it feels clunky. I'm never going to say a 30 degree, 60 degree, 90 degree. If it's just implied, we're talking 30, 60, 90 degrees. Okay, now, if we wanted to obtain this, and again, no spoilers for your stuff, I just want to make sure that we have it. If I were to draw a 30 or an equilateral triangle, and I know it's not the exact same, and I'm going to make that a little bit nicer. And it's not going to be perfect, but do you guys believe that this is an equilateral triangle? So even if you didn't, now you do. I'm not going to keep those marks, but now they're all the same. They have to be. Okay. What is every angle on that triangle? 60 degrees, and like every triangle that lives in flat land on paper, what do the interior angles always add up to? 180. Cool, that's a triangle angle sum theorem. I'm only going to label one of them. I know that that is 60 degrees right there. And I know that it's that way on every vertex, but I'm only going to write one. If I gave you one of these, or if somehow you're able to have a physical 30, 60, 90, or a 60, 60, 60 in front of you, would this point fold onto itself over here? Like, could I fold the triangle in half such that it lands on itself? We could. Now, there'd be a crease on your page, and I'm not ruining anything, just so you know. This is no more than I gave you. You would wind up with a crease right here. And what would this angle down here be? 90, which would in turn mean this one up here has to be what? 30. Okay, so we could obtain a 30, 60, 90 from this, right? Okay, we didn't, like this is varying size on your screen, right, if we're all watching on different devices. So let's just call it some, I don't care what they are, some unit that we're dealing with. What would be the most convenient length to say that this length here is? Every length. Like we could say they're each 3.972, but that would suck. What's a better number to use? Could every side length be 1? Like it would have to be, right? If we just say 1 is 1 unit, then all 3 sides have the same length. What is this length then, opposite from this 30-degree angle? It would have to be 1/2. Because I can see I literally took that piece and I just folded it into 2 equal pieces. Okay, here's the big, I don't want to say challenge to this. It is not obvious even if you have one in front of you. I want you guys, for me real quick, find me the length of the other side. The altitude, that crease that we've drawn. I want to know this length. Cool. We're getting Greek with it. Pythagoras was Greek, if you guys didn't recall that. Cool, and I'm going to draw another one below, and we'll talk about this here in just a second. I don't want a decimal, just so you know, I want an exact answer. You can check it with the decimal, I don't have issue with that, but I do want an exact answer. What are you guys using to find it? The Pythagorean theorem. Okay, so help me out here just to make sure that we can all agree. And I just took this triangle out just so you know. I'll use these numbers here in a second, the 1 and the 1/2, we'll make sense of it. What is, I don't know, what's the shortest side? Here, here, here. Shortest side is opposite the smallest angle, so we'll all agree that this is the short leg. What's the longest side of a right triangle called? Here's my hypotenuse. And how about over here? We have short leg, hypotenuse, and the long leg. Okay, doesn't matter how my triangle is oriented, not long lead. Doesn't matter how my triangle is oriented, not even a little bit. I just need to be able to see this is a 30-degree angle, it's opposite the short leg. Okay, now, in your Pythagorean theorem, it got a little ugly for a second, I bet. Why did it get a little bit ugly? The decimals or the fractions, however you want to think about it. I agree. I know that the Pythagorean theorem, I'm just going to call this y for now because it's a vertical. I know Pythagorean theorem would read 1/2 squared plus y squared equals 1 squared, right? And this is a little bit cumbersome, the fractions. I think we can all deal with it, but we're going to double check real quick. What's 1/2 squared? A fourth. Okay, so we have 1/4 plus y squared equals 1 still. And then what? How would we continue on? I'll work this way. I'm going to erase this in a minute, or not. Subtract what? Okay, so I'm taking a big step here. Are you guys okay if I call it 3/4? All right, and one more step and we're done with it. Okay, anybody know the square root of 3 off the top of your head? Yeah, me neither. How about the square root of 4? Okay, so it would be root 3 over 2. Okay, now this is doable. We're going to generalize this though. I'm going to make a claim, and I'm pretty sure this is physics now that I'm talking about it in more depth. I'm going to make a claim. I want everybody to internalize this. For a 30-60-90, the short leg is king, or queen, whatever, dictator. Don't care what words you think of in your head to make sure it's the most important. The short leg is the most important. So hypothetically, if we use this example, and this one's going to be a little bit harder to see, but I'm going to put that length in there. That was root 3 over 2, right? Okay. When I look at this, if I said the short leg was x, knowing that it's 1/2, to go from the short leg to the hypotenuse, does it seem like there's an easy option? And even more, this is so much easier of a, nope, I'm just going to leave it there. I don't want to spoil it. How do we go from a length of 1/2 to a length of 1? You double it. And if we think about how we got this triangle as well, like this length was 1, right? And I literally just folded it in half, and I got half of it. Okay, so if the short leg is x, what's the long leg? Sorry, the hypotenuse. 2x. Okay, a little bit harder to see. I multiplied 1/2 times 2 to get there. That's clear. What did I multiply 1/2 by this time? Careful, there was already 1/2, right? So the question, and it's just weird when we see it written out, and it's strange to word, don't write this yellow. 1/2 times something, I'm just going to leave a blocks here, times that equals root 3 over 2. What must have been in this box? Root 3. So we just took the short leg and we multiplied it by root 3. And that wound up dividing by 2 in the process. Which means in this general case, it'd be x root 3. Okay. I remember this for a very specific reason. How many angles are different in a 30, 60, 90? So give me a number. 3 angles different, root 3 shows up. Okay, in contrast with this, your 45, 45, 90s, that part was just to feel that early victory, because those ones are pretty easy to do on there. But I promise they do show up as well. This rule will always work for right triangles. You saw this in geometry. I imagine you saw this in Algebra 2 last year again some more. You're seeing it here. This is your shortcut. If you want to take the time or you want to come to me to get the help, we can write out a short to long, long to short, like we can do all of them. But this picture tells everything that I need. Okay, just to keep my notes nice, you recall another special triangle? 30, 60, 90s, we just worked out some shortcuts with it. What was the other special triangle I made you guys make? A 45, 45, 90. Now, I called it something different at the origami session. It was an isosceles right triangle, but they would have the same length, and it's still the same thing. It has to be this. Okay, to draw a 45, 45, 90, I'm going to go ahead and draw it slanted like this for no particular reason right now. Now, same thing can happen here. And I want you to do a little bit of scratch work off to the side. If we just nicely said that, oh, this length is, I don't know, what do you want this length to be? Sure, seems reasonable. If that length is 1, what's this length? So both legs would be 1, right? It's isosceles, 1 and 1 here with 45 and 45. I want you to find me the hypotenuse real quick as well. This one's much faster. Root 2. 1 squared plus 1 squared is 2, and the square root, root 2. Okay. I don't remember if you mentioned the lower. This was a super controversial idea when Pythagoras and his clan mates, or rather cult mates, were going through it. People died when this was proposed. Like, they literally killed them because, nope, that number's not nice. Sorry, peace out, dude. Okay. Now, in reality, there's an easy way to do this, that if we change the numbers, it might be a little bit more clear. But we're going to generalize this one all the same. I know these two are the same, right? If we change this to x, run through the Pythagorean theorem again. And you don't have to change it on your paper. I'll do it here. You should have some scratch work, but we're going to put the other shortcut right here for our 45, 45, 90. I want you, instead of using a length of x, I want you to use, a length of 1, I want you to use the length of x. X there and x there, and run through the Pythagorean theorem for me again. If you write it down, I would have a better idea of whether I agree with you or not. And you'll see in a second the issue that I might have had. I don't know if I really had an issue or not. I can't tell. You're good. Nothing erases there. You're good. Keep rolling. Really? Yep. No, just add the left side, and then you're going to solve for x. Or for c, I'm fine with as well. Where do you go next? X squared plus x squared. Good. Where's the x? Okay, just to check, I'm going to show the scratch work over here. I only looked at a few pages, but I saw x squared plus x squared. Is this your phone? Okay. I thought that it was Brent's just based on the number. It's been buzzing like crazy. Cool. X squared plus x squared equals, I don't know, what do you want to call it? C is pretty natural for people. I'm okay with that. What's x squared plus x squared? So I get 2x squared equals c squared. If I want to solve for this side here, how do I solve for c? Okay, we're going to be real careful with this because there's some square root properties. I have the square root of 2 times x squared. Can I split up a square root if it's a product underneath? Do you know the square root of either of those numbers that we used in that product? I know the square root of x squared. What is it? X, cool. So that'll come out, right? The square root of x squared, I get an x out. Anybody know the square root of 2? It's just that, right? Now, for this, we are going to use the crap out of this shortcut over and over and over and over. As we look at this, if you are given a side of a right triangle, for example, you just multiply by what to get to the hypotenuse? sorry, if you're given an isosceles right triangle, if you know the sides, for example, this was a side length of 10. What's the hypotenuse? 10 root 2. Now, you multiply to go from leg to hypotenuse. Could you go the other direction? Hypotenuse to leg. And you would just do what instead? You would divide by root 2 to get it to fall back out. Okay, we're going to use these shortcuts like crazy. And we're only going to deal with one little section of the unit circle today. Now, just so you guys know, you're going to hear me refer to this idea. And before we move on, these shortcuts, I hope you remembered them, but I get it if you didn't. Do you at least remember seeing these shortcuts? Was it in geometry or algebra 2 or both? Okay, so I'm hearing both, and that's like, I heard some people say geometry, some people say algebra 2. I'm fine with that. Cool. We're going to think in a bigger sense. Do not draw this right now. If I were to think of a circle centered, that's not very circular, but that's okay. If I were to think of a circle, you're going to hear me reference bow ties and butterflies like 1,000,000 times. You guys know what a bow tie looks like? Okay. Now, check it out. When we draw triangles in a circle, like we're going to be doing a lot of, we have two ways to do it. I could draw this triangle like this, or I could draw it up here, and I'm not even going to draw it because it's such a bad way to do it. This would be my angle that we turned at. Now, if we wanted to, and we will, and we'll do the whole one later, and I promise I need to better circle. That's not going to work. Hey, I have a circle right here. Okay, it's going to be annoying, and like the contrast is different in colors, but whatever. So check it out. The bow ties and butterflies that you're going to hear me reference, which we will draw the whole circle eventually, show up here. If I were to draw a bow tie on this, and I'm just going to pick any arbitrary point on it, it could be here. Do you guys agree that this is a bow tie? Or if you add antenna, it's now a butterfly, right? This is my idea of bow ties and butterflies. What I really want you to focus on is how many triangles did I just, how many, that's a weird question. How many triangles do you see on the board? I see 6. But at least 2 or 4. Okay, so just to show you the 6 that I see, and Abigail, you said 6 as well? Okay, check it out. We're going to see if this works. Moment of truth. Is this going to shade the triangle or just one little square? Weird, but okay. There's 1. 2. I don't get it. Not a clue. It doesn't. There's 4 that people probably saw. But if you're feeling like super crazy, that's a triangle. That'd be the 5th one. And the 6th one would just be on the other side. Okay, I like 4 as an answer. There are 4 triangles on the board right now. The green triangle extends into which quadrant? 1. We go to a point on the circle and we drop straight down to the x-axis. The yellow triangle lives in which quadrant? Notice though the language doesn't change. I draw my radius out to the circle and then I drop straight down to the x-axis. The blue triangle's in the 3rd quadrant. I draw the hypotenuse out to the center, out to the circle, and then I go directly up this time, but to which axis? I draw this out. That's not the right thing. I draw it out here to the circle, and then I go to the which axis? X-axis, and it happens in all of them, right? These are the triangles that we care about. Bow ties and butterflies, we will always draw them this way. Okay, now to start putting things together, we had 2 special triangles, and we're going to be referencing these shortcuts. I'm not going to give you homework tonight, just so you know. I'm going to cheat on this. If you want to draw as nice as you can a quarter circle, please feel free. I'm going to make it nicer and look like good on my page, but I want the axes, I just don't want numbers. Cool. I'm only taking quadrant 1, only one that I care about for now. I'm going to make it way bigger. Yours doesn't have to be gigantic, but you are going to have to draw at least a little bit in it. all get a larger circle. All right, so there it is. Now, when we measure angles, anytime we're talking about circular measures and stuff, we always start at the positive x-axis. That is our initial side every time. Now, there are 3 special angles that show up, and this picture is going to look kind of messy by the time we're done with it, but we'll have a nicer version in the end once we cover everything. There were 3 other than 90 degrees, 3 angles that we saw a moment ago on those special triangles. What were the other 2 angles that weren't 90 that showed up? 3 angles, I'm sorry. 30, 60, and 45, right? Okay, we're going to look at just one of them initially. Let's start with the smallest one. It seems natural. I'm going to estimate here. It's not going to be perfect. I'm going to draw a 30-degree angle from the horizontal x-axis. Probably about there. I think that's where it lives. Now, just to front load this a little bit, I know that this point on the circle has some coordinate. It's an x and a y. Everybody good with that? Not writing it down, I just want us to be aware that there is an x and a y. If I follow the bow ties and butterflies rule, and even further, I include that this is 30 degrees, could I make my nice bow ties and butterflies triangle out of this? Where would you want me to put my pen and to draw a straight line in which direction? So at the point and straight down. Here is my bow tie and butterfly. Now, it wraps back to physics, which physics people, I think, will be more comfortable with it, but we'll see. I have a 30-degree angle that forms that triangle. What's the hypotenuse of this circle if it's the radius of the circle if it's the nicest possible circle we could deal with? 1. 1 is the nicest radius that we could pick. That's what we wind up with on the unit circle. Using your shortcuts, I want you to help me with something real quick. 1 is the hypotenuse in this triangle. It's the radius. No matter where I draw a triangle using bow ties and butterflies, it's always a radius of 1 if we use this circle. How do you go from here to, I don't know, in this situation, the long leg, which is down here? Check your shortcuts. When we talked about it, we went short to hypotenuse and vice versa. And maybe we'll go to the short leg first because that's a little easier. Let's do that. I want to find this ordered pair right off the bat. Let's find the short leg first. On a 30, 60, 90, based on what we have written, and I can even go up and show us, if the hypotenuse is 2x, how do you get to the short leg? So careful. Here's the short leg. I think that your first step was enough, Rafa. If I know that I multiply by 2 to get the hypotenuse, I just divide by 2, right? Okay, help me out here. At 30 degrees then, what is the y coordinate, which coincidentally is just this short leg? 1/2. Everybody okay with that idea? Okay. Super cool things about to happen. What about the other one? Now that this is 1/2, and I know that that's 1/2 vertically, that's the king, the queen, the patriarch, matriarch, dictator, president, don't care what you think. How do you go from short leg to long leg? Say that again. Are you sure? To go from short to long, I multiply, right? Which, if you take 1/2 times root 3, and we clean it up, it's root 3 over 2. Okay. I'm only using the special triangle rule. Everybody okay with that? Okay. I'm going to do another triangle on this, but we're going to do a little bit bigger triangle. We had 3 special angles that we saw. The smallest was 30. I'm now going to add to this, and that one's, sure, that's really where it is. Is it? No, it's right there. Okay. What's that angle that I just formed? 45. Now, it's hard to draw it out in yours, and I get that. We will clean it up nicely. I'm looking at the purple triangle now. Could I do the same thing and just drop straight down? Just like this. And I'm not even going to add my 45 degrees. We'll add all that stuff eventually. It's going to make mine super ugly. Did I do anything different? I mean, no, the angle's different, but the same idea, right? Okay, now we're working on the unit circle. What is this distance from the center to this point that's also some point x, y that we're going to find here in a minute? It's still 1, right? It's a hypotenuse. Check your rules that we just developed for a 45, 45, 90, which I guarantee that's what this is because we dropped it straight down. We have a 90 degree. If I have the hypotenuse is 1, how do I go to either leg? And we can work it the same way that we thought about the other one. To go from leg to hypotenuse, what did I do? I multiplied by root 2. So if we want to do the exact opposite, this direction, what would I do? Divide by root 2. Now, this, I don't want you to write this yet. We're going to talk about this. This is what you would get, right? Is that allowed? Why? So I can divide by it, but I can't keep it that way. Okay, full disclosure, you totally can. And this is last year that you won't be allowed to. Okay, stuff is pretty, it's ugly that it makes everything nice. Last little step, this is root 2 over 2 when you clean it up. The other side, because it's an isosceles, is also root 2 over 2. I lied, you have one little homework. You're going to do the same thing once more for me, but you're instead going to go all the way up here at a 60-degree angle with a radius of 1. I need you to bring me back this ordered pair tomorrow. Cool. That's all you have for homework. Laters. If anybody's dying to see the equilateral triangle, don't Google it. I'll show you tomorrow if you don't come up with it by then. Cool. Thanks, guys.